Hello everyone, it's Calder from 19. Today's day 96 in my challenge day. In the previous few videos, I set up the HLSL compilation to the Spire B to use it as a Spire B output in my Vulkan application. But as you can see, my Visual Studio doesn't interpret the HLSL syntax at all with a bunch of red underlines. But there's no problem in this HLSL code, and I can build it with the DXC compiler, but I don't know why. So instead of just sticking into this problem, the setting up the things and debug some the, why this happened, I can use GLSL right now. So I'm gonna stick with the GLSL for the just right now, and then let's apply the HLSL usage in the later on the application stage. Mm, so we can run the application, but I don't know what is this problem. Now this is a SparB format error. So my next plan is to apply the computer shader and the ray with the ray query extension in this GLFW windowing system. Also, but today I'm going to look back around the theory part, which is the BLDF and the rendering equation in the physically based rendering. I found a really good mastering course in the YouTube by Dr. Kalajoy. I don't know how to pronounce his name, but let me show you. Wait. During two.
OpenAI built.
So the series made by these 2 minutes paper YouTube, he just rebuilt his lectures in the True Win University for the mastering student.
We are going to.
So these courses is based on the physically based rendering book, which is a PBL book in that you can see in the online. But the book is kind of the references to get to know the what is the inside the algorithms. When you want to understand the algorithm in the deeper, it is a good book for the reference. But when I read it, uh, because they wrote the book with when they write some program for the PBLT as a documentation, it released in the online. So there is some of the gap between the good book and the documentation. But he just these courses summarize it that uh, maybe compact then summarize. with an easy explanation. So I just see this BRDF tutorial, no BRDF
Now, there's
in the last night, and I really liked it. So honestly, it's kind of old because at the 9 years ago, but the fundamentals always important, and I think this will be a good fundamentals for me to understand the later papers. And also, I saw the really interesting papers.
open
Simulation of functional is possible.
How many times have I felt this?
Yeah. So this is the new papers for the restore to enhance the time, enhance the anti-aliasing and the frequency noisy in the rendered scene. So this is a previous technique with the common restore algorithms. But as you can see in the image, there are high frequency of the noisy and also the anti-aliasing. But in the right image with the area restore, the anti-aliasing is reduced and frequency also reduced. So we are on the era that reaching the real-time ray tracing techniques, and I'm really interested to learning everything. And I think to understand this kind of the state-of-the-art papers, we need to learn the fundamentals first.
OpenAI. Now, there's another fundamental question, which is what makes the difference between different materials? And the other question is, how do we model it? Well, different materials reflect incoming light to different directions, and they
And I think this can be a problem with the copyright because this is his video work with a lot of effort. So I will not show this video in my recording scene. Instead, I just with opening up my CD notes. So if you're interested in to learn some rendering courses in the master student level, you can search the two win rendering courses in the YouTube, and you can always check this video because this is all free. And I'll move up the scene on the next monitor. Okay. Return rendering. BRDF.
They absorb different amounts of it in different wavelengths. That's the answer. We are going to talk a lot about this, but this is an example. These are different material models. So the specular, in the specular case, there is
Let's not forget to add a reference first.
one incoming direction and there's one possible outgoing direction. That's it. This is what always happens. This is, for instance, a mirror, because I
One possible outgoing.
see exactly the reflection of myself. There's no other thing that I see in the mirror. But for a diffuse surface, for one incoming direction, there is many possible outcomes in many possible directions. And this gives a diffuse surface. We're going to see examples of that. And it writes spread. Please forget this term. Let's call this glossy instead, because this is what it is. This is like the mixture of these two. So these are some basic material models that we are going to see in our renderers later on. Now, to formalize this in a way, let's create a function that's a probability density function with 3 parameters. So this is a 3-dimensional function. One variable is the incoming light direction. The other variable is a point on the surface, and what I'm interested in is how much light is flowing out from this point in different directions. Now, a bit more formalized, this FR is going to be this function. I'm interested in the incoming direction and the point in space. This 2 is what I have, and I will be interested in the outgoing directions. What is the probability of different outgoing directions? And this is how we will write it formally. Omega is an incoming direction. And this is how, what is the probability of different outcomes I have? And I will be interested in the outgoing directions. What is the probability of different outgoing directions?
Probability.
And this is how we will write it formally. Omega is an incoming direction. Direction x is a point in space that we choose, and omega prime is the outgoing direction. And this we call the BRDF, or bidirectional reflectance distribution function. So this is a very complicated name for something that's very simple, BRDF. Now, what about materials that don't reflect all incoming light? There are some materials that transmit some of it. So for instance, glass, water, gemstones, and such. Well, it could look like that, and here above you can see some BRDFs, and below you can see something. Because it's not reflected, it's transmitted. There are some materials that let them through. So here's an example. Well, everyone had seen windows and things like that. So it's not reflected. It's transmitted. There are some materials that let them through. So here's an example. Well, everyone had seen windows and things like that. Well, the question is why, like, just a physical question, why are these objects transparent? Sorry?
They transmit the light.
Yes, they transmit the light, but what is happening? happening here exactly? So just some physical intricacy that the most fundamental question, what is inside of an atom? And the best answer is nothing. Because an atom is 99% empty space. There is the nucleus, which is, so the whole atom is the size, for instance, of a football field, if you imagine that. Then the nucleus is a small piece of rice in the middle of the football field. That's the nucleus. And the electrons are also very small things, like small rices, which are orbiting this nucleus from very far away, like the sides of the football field. And in between, there's nothing, absolutely nothing. So the more interesting question would be, why is not everything transparent? I mean, there's absolutely nothing in there that would divert or absorb the light, right? Everything should go through. Why is not everything transparent? Not only glass, but everything. And the reason is absorption. So these electrons are orbiting the nucleus. And what essentially is happening is that electrons can absorb photons. Photons electrons electrons can absorb photons. Photons are, if you imagine light as not rays or not waves, but particles, then photon is the base. Basic particle of light. So electrons, they absorb photons. And if they do, they go from an inner orbit, like a lower energy level, they jump to a higher energy level, because it's basically you after lunch. You eat something, you get more energetic, you get more jumpy, so it jumps to an outer orbit from the nucleus. It's a bit further away. So it absorbs the light, so the light doesn't go through. So this is why most things are not transparent. But the question is, why is then glass transparent? And the answer is that these orbits, these different places around the nucleus, they are so far apart that in the visible light spectrum, if the electrons absorb a photon, they don't get enough energy to jump to the next orbit. In the visible light spectrum, if the electrons absorb a photon, in the visible light spectrum, if the electrons absorb a photon, they don't get enough energy to jump to the next orbit. And this is why most of the light is going through these glass materials. And the interesting thing is that this is not always the case. This is the case for visible light spectrum. There is another spectrum which is absorbed. So if you have a spectrum that is a higher energy spectrum, then it may give enough energy for this electron to jump to a different orbit. And we can easily find out what spectrum it is, because, for instance, we use glass for a number of different beneficial things. Well, for instance, you cannot get sunburn if you are inside of the house and you have your windows closed. And we are wearing sunglasses in order to protect our eyes from something. So is there someone who tells me what this spectrum is? Exactly. Just a bit louder.
Ultraviolet.
Ultraviolet, exactly. So ultraviolet is a spectrum with a higher amount of energy. Yes. And if you absorb it, then this jump is possible. So this is why it is absorbed. So just some physical intricacies. So lights may get reflected. If we have a material that most of the time reflects light, then we call it the BRDF. The R is the interesting part, that's the reflection. And if transmittance is possible with the material model, we have the BTDF, which is the bidirectional transmittance distribution function. And as an umbrella term for both of these, this is basically the whatever term, is BSDF, so bidirectional scattering distribution function. I'm not saying this because this is lots of fun. I'm saying this because you're going to find these terms in the literature all the time. So BSDF is basically things that reflect and things that transmit. Okay, what are the properties of BRDFs? And after this, we will suddenly put together something beautiful very rapidly. So there is Helmholtz reciprocity. It means that the direction of the ray of light can be reversed. What it means mathematically is that I can swap the incoming and outgoing directions, and I'm going to get the same probabilities. So the probability of going here to there is the same probability as coming from there to here. If I look at things from both sides, I will get the same probabilities. So that's often useful in physics. Positivity, this is self-explanatory. Well, it cannot be less than zero. A probability cannot be less than zero. For every outgoing direction, there is some positive probability or there's zero. That's it. Nothing else is really possible. So formally, this is how it looks like, and it makes some mathematicians awfully happy. And there's energy conservation, perhaps the most important property. An object may reflect or absorb incoming light, but it is impossible that more is coming out than the incoming amount. Well, obviously we have light sources and things like that, but we are talking about strictly material models. So this means that if I integrate this function for all possible incoming directions, then I get, if I take into consideration light attenuation that we have, we have talked about. This is why it is so hot at noon and why it is so cold at night. Then I'm going to get 1 or less. And this is because if it equals 1, then this means that this kind of material reflects all light that comes in. And if it's less than 1, then this means that some amount of light is absorbed. Okay, we are all, then this means that some amount of light is absorbed. Okay, we are almost there at the rendering equation. Generally, what we are going to do is that we pick a point x, and this direction is going to point towards the camera or my eye. This basically means the same thing. It's just an abstraction. And what I'm going to be doing is I'm going to sum up all the possible incoming directions where light can come to this point, and I'm interested in how much is reflected towards my direction. And let's not forget that objects can emit light themselves, and we will also compute this reflected amount. Of light. So, just intuition, light exiting the surface towards my eye is the amount that it emits itself, if it's a light source, and the amount that it reflects from the incoming light that comes from its surroundings. And this is how we can formally write this with this beautiful integral equation. Let's tear it asunder and see what means what. This is the emitted light, so this is light from point X going towards my eye. How much is it? Well, the amount that is in point X emitted towards my eye, if it's a light source like that one, then I definitely have this amount. And there is an amount that I reflect, that is reflected. Let's see what's going on. This is what I just told you. And again, and this is the integration integration. This is the interesting part. So I'm integrating this omega prime. So all possible incoming directions, what you have seen the hemisphere on the previous image. Hemisphere means basically one half of a sphere. We are integrating over a hemisphere, not over a full sphere, because if we take into consideration the cosine, if the light comes from above, that cosine 0 degrees is 1. And as I rotate this light source around this point, then this cosine will get to 90 degrees, so from here to there, and the cosine of 90 degrees is 0. Therefore, there's going to be no throughput if it comes from that direction. And if I have something that's higher, that would be negative. We don't deal with these cases. So this is why I'm integrating over a hemisphere. So sunlight is coming to this point in different directions, and what I'm interested in is how much is this light is reflected towards my eye. This is multiplied by the incoming radiance. There's the BRDF, and and light attenuation. That's it. This is still a bit difficult. This is still a bit elusive. So first we are going to train ourselves like bodybuilders on smaller weights. So we're going to create an easier version of this. Because apparently this is terribly difficult to solve. If you take a look and if you would sit down and try to solve it for a difficult scene where you have objects and geometries and different BRDFs, different material models, you will find that this is impossible to solve analytically. And one of the first problems is, yes?
This equation is just for one point, right? So we are looking at one point and then we want to calculate.
Exactly, yes. And here comes the catch. So I'm interested in how much light is going towards my eye from this point. How much is it? Well, it depends. If I turn on other light sources, then this point is going to be brighter, because the radiance coming out of this point depends on its surroundings. Is the window open? Are the curtains pulled or not? So X, this point X depends on this other point Y, for instance. All other points. Then we can say, okay, let's not compute this X first, let's compute this Y point instead first, because then I will know X. Okay, but this Y also depends on X, because how bright light is on the other side of the room also depends on how bright it is in this side of the room. So there is some recursion in there, and it's if you don't think out of the box, this is impossible to solve because you don't know where to start. This integral is hopeless to compute in closed form because there may be shapes and different objects in there, and this will make integration immensely difficult. The integral is infinite dimensional. Later you will see that if I compute one bounce, this x that I have been talking about, that's okay, but I need to compute multiple bounces. I need to start tracing rays from the camera and see how much light is entering the lens of the camera. But one bounce is not enough. Is two bounces enough? So after the x, I continue somewhere else. Is this enough? Say something. It's not enough. Okay, but I think maybe 3 is enough. Is 3 enough? It's not enough. Okay, well, you guys are very picky. Okay. Is 10 bounces enough? Okay, why not? Because there's still some amount of energy left that if I would continue this light path, I would encounter other objects, and I don't have any knowledge of that. We need to compute an infinite amount of bounces. Even 1,000 is not enough. So, and this rendering equation is going to be 1.1 bounce. And if I want to compute the second bounce, that's going to be embedded, there's going to be embedded another integral equation, another rendering equation. And this goes on infinitely. This is the biggest equation in the whole universe. It's impossible to solve. And it is often singular. I will later show you why. So even if you would want to integrate it, you could. So this is horribly difficult. This seems impossible. And apparently, at this point, we cannot solve it. So this is the end of the course. And we have an impossible problem. There is no reason even to try. And goodbye, see you, never, because there's never going to be any more lectures. But in order to understand what's going on, first we're going to put together a simpler version of this equation that we can understand, and we can work our way up. There's another formulation of the rendering equation. I'm not going to deal with this too much. You can imagine this other version as moving points around. So There is a light source in P3 and there is the sensor at P0, and this is one example light path. And what I'm doing is I'm not stopping at one point and integrating all possible incoming directions, because this is what I did with the original formulation. What I do is I compute one light path, I compute how much light is going through, I add that to the sensor, and then I move this P2 around. I move it a bit, I compute the new light path. How much is going through? I move this P2 around again. So imagine this moving everywhere. And imagine also P1 moving everywhere. So all these points are moving everywhere, and I compute the contribution of this light source to the sensor. So this is another kind of integration. I'm not going to go through this. What is interesting is that there is a geometry term in there, and this describes the geometric relation of different points and light attenuation between them. I'm not going to deal with this too much. I just put it here because if you're interested, then chew your way through it. In literature, they often write it this way. Let's go with a simplified version of the whole thing.
Before I'm going to stop recording, let's recap what I learned today. So the first thing is that I learned is the material model in the rendering, uh, in the physically based rendering. So first, the material can have a specular reflection and a diffuse reflection, and the two mixture of the specular and the diffuse. Because we are not considering the transmittance effect, because it is not reflected to our eyes. So maybe our eyes is behind the transmittance object. It can be have an effect on the color of on the color of the surface, but to simplify the problem, we are not considering the transmittance here. So specular reflection only have one possible outgoing direction against the incoming light, and the diffuse reflection, on the other hand, can have many possible outcomes, many possible directions. So it can generate many combinations, and one of the combination can be obtained by smart random sampling in the implementation side. So next thing is the probability density function. Because the light is reflected on the surface, so we need to calculate. We need to know. We want to know that what is the probability of the outgoing direction against these incoming lights. So, but this is not the case of specular reflection, because specular reflection just reflect the light uh, at the same angle with the incoming angles against the normal vector of the surface. So it is not the case of the specular reflection, but for the diffuse reflection, we're curious about what is the probability of the outgoing direction. So three parameters are required for uh, this probability density function. So the one is the incoming light direction, obviously, and the point on the surface, because we are caring about, we are caring about just a single point when we compute something. So we need a point on the surface, and also we need the outgoing direction as output direction. So when we call this function, this output direction is uninitialized, but after we call this PDF, this PDF compute the outgoing direction against the incoming direction, so it stores the value inside the out direction. So this tells us about what the probability of outgoing direction in given interval. So formally, it could be written with the incoming direction at the point of the surface and the outgoing direction as a storage. Where the omega with prime is outgoing direction here. So this is our BRDF model. So by with this reflectance probability density function, we can compute all of the outgoing directions against the incoming light. So what if the case a light transmits the surface? It can be modeled with the BTDF, with the T of the transmittance can be defined for this in this case. So the BTDF takes the case about like this, like below. So roughly, so BSDF or BXDF is combination of BRDF and the BTDF. So we combined this BRDF for the reflectance and the BTDF for the transmittance. So we can make an effect of the light scattering effection on the surface by combining two these of the model. So this and there's a quick note for optics. So every material is composed of the numerous atoms, but atom is composed of 99% empty space. Think about the football at the center of the football field. The professor takes this example. Then why everything isn't transparent if they are composed of empty space? The answer is light absorption on the surface of the material. So there are electrons around the nucleus of atom, and they can absorb the photons. Seeing a photon is a light in the perspective of a particle-like property of the light. So actually, a light can have both property of particle-like property and the wave-like property at the same time, because uh, it moves by having an energy, but at the same time it has a particle. So a light, we can say that a light is have a quantum property itself, but because of my lack of the physics knowledge, so I can't ensure that all of the knowledge of the optics, but yeah. Anyways, but why glass is transparent? It's because the orbit of electrons are different dependent on the materials. In this case, in the case of glass-like materials, the orbit of electrons is too far to get enough energy to jump into different orbits so that we can't see the reflectance. Uh, yeah, so it is too far to absorb energy. So just the light just passing through the surface, which is the transmittance we say. But note that is just this diffraction described in the context of the visible light spectrum. And there are a lot of light spectrums, so some of the spectrums can be observed in the surface, even if it's like a glass-like materials. So what properties are there in the BRDF? So first is reciprocity of the surface. So the direction of the ray of the light can be reversed. That means that we can swap incoming direction and the outgoing direction. Yeah. So the equation is written in the below. And the next thing is a positivity. Positive positivity. So this is just obvious because this is one of the axioms of probability, because the BRDF is basically a probability density function, and the probability can be non-negative. There is no negative probability. So next thing is the last thing is the energy conservation, and this is the most important property. So it is impossible to reflect more than incoming light energy. So we're taking care of this integral term by incoming all the direction omega, large omega, and we have a BRDF function. And by adding this cosine term, uh, we can taking care of the light attenuation of the incoming light. So based on above equation, we add up the incoming energy from all directions. So if the result of the integral is equal to 0, equal to 1, all light is reflected. Some kind of ideal mirror-like materials. And otherwise, less than one case, some light absorbed to the material. So more than one is impossible. And finally, the beautiful rendering equation. So by combining to understand the rendering equation, we need to know that the object can absorb the light energy, and the object can reflect the light, and object can emit the light. So by combining all of them, we can write down this beautiful rendering equation. So exciting radiance in point x toward the direction w, direction omega, is dependent on the emitted radiance of the same direction, and the sum of incoming radiance from all incoming directions, and incoming, sorry, yeah, about outgoing direction, and the incoming radiance from direction omega prime, BRDF term, and the light attenuation. But this equation is almost impossible to solve in closed form because when the scene is going to complex, the dimension of this integral going to the infinity because the ray tracing algorithm basic is basically the recursive algorithm where it depends where the specific point x depends on all of the other all of the other points in the light path, and we have a lot of the light paths in our scene. So this is practically is impossible to solve in the closest form. So in this case, we use the Monte Carlo integration, and I think we're gonna learn about this in the few lectures later. So this is all for today's recording, and thanks for watching. See you next video. Bye bye.